Now, these regions in space are dictated by the probability function, the Schrodinger equation squared. So when you look here in front of you, what you can imagine is if you were to take a snapshot or several 100,000 snapshots of an atom, and each time put a dot where the electron was located, you might see a scattering something like this, where the electron most of the time, the most probable location was in close to the nucleus. So this is just a single electron around a nucleus. But yeah, there was times when the electron was farther away. And in theory, the electron could be located at infinity. It would be a very small probability, but there would be a probability there. Well, what we need to do is kind of confine our region in space here. So we're going to take that function, and we're just going to consider the part of the function that contains a 90% probability of finding the electron. So in this case, it's going to define a spherical region. Now, if we take the equation and we look at different energies, all right, so we alter some of the variables in the equation to account for the different energies that we experimentally see for the electron, we come up with some other shapes for orbitals. Now, these are going to get a little complex. Don't get fearful for them. But what you want to remember is that each of these shapes are based on experimental evidence in regard to the energies that the electron possesses. And then that data is put into the Schrodinger equation, and these shapes are then generated from that. So we have something called p orbitals. And so p orbitals are, again, regions in space. These time, instead of being spherical, one single p orbital has a dumbbell-shaped surface. So if you look over on the left, this entire area is the p orbital. And you see that for the p's, again, it shows the kind of the cloud model there with the dots to the left of that. And then the more solid boundary that we would look at if we were trying to kind of understand this a little better. You notice that with this dumbbell shape, there are 3 orbitals that are at the same energy level. When they're at the same energy level, we say that they are degenerate. And so each of these dumbbell-shaped orbitals would be oriented along, perpendicularly along each of the coordinate axes. So one along the x, the z, and the y. It's important to note that each orbital is capable of holding 2 electrons. So again, what we're going to do is we're going to work towards trying to understand what regions in space the electrons occupy. And so as we look at atoms, we're going to take the number of electrons they have, each individual atom, and see how they fit into these orbitals that are described by Schrodinger's probability functions. And then at the bottom, as if it's not complicated enough, we have what are called d orbitals. D orbitals have 4 lobes to them. And again, it's going to get a little complicated because how do you feel the electron in 4 different places? And it's a wave property. It's a wave characteristic, and something that we're not going to fully understand until we take more physics. But there in the d orbitals, you see there are actually 5 different types of d orbitals. Again, regions in space where the electrons could be located. And so our next task is to take each of the elements and try to imagine where the electrons are fitting into these regions in space that are called orbitals.